Hi everyone, welcome. I'm Valentin and I work for Google Cloud in Paris. I'm super excited to be with you today. Today we'll talk about performance and we'll talk about performance of software written in Go, running in a public cloud. You may or may not believe this, but I have an accent. I am French, and yet today I will present in English, so if you are French as well, please excuse my English. And if you are English speaking, are there English speaking only people in the room? Okay. Please excuse my French. What I say today applies in general to most cloud computing performance concerns and most Go software programming. It is not specific to a vendor. However, my examples will be illustrated with the Google Cloud Platform infrastructure. First, I'll share my insights about what we want to optimize and why. Then we'll see how we can observe the performance of a cloud architecture and discover which components best explain the actual latencies experienced by our users. Then we'll have a look at how we can observe and improve our components written in Go. Finally, I'll share my list of top 10 favorite performance problems and solutions. So stay tuned. What is performance tuning? It's usually about working on something slow and making it faster. Pretty simple. And that's mostly what my talk is about today. Why are we doing this extra effort? We might want to increase the throughput and to decrease the cost. But today I'm focusing on the most important goal, which is to offer a better user experience. Human seconds are most precious than machine seconds. Users have very high expectations of speed, and if they experience a slow service, they'll be frustrated and they will leave. The architecture of a new software system designed for a certain level of performance is always the result of experience and intuition. They reflect what kind of latency we should expect in theory. However, measurements are more relevant as soon as a system exists, even before its initial release, and measurements often contradict intuition. I'm an experienced developer and I have intuitions. Well, most of the time they are dispelled by the actual numbers. So on one hand, I get frustrated that my super smart intuitions turned out to be dead wrong. But on the other hand, I'm happy and grateful that my measurements finally provided me with insights closer to the reality. There is an interesting correlation between code quality and performance. Making your code clearer and more decoupled also makes it faster at first. On the other hand, the more you push your quest for performance, the more you will resort to hacks and complicated code. It's a trade-off. How far are you willing to go? Now, improving the performance is not a great deal if we break the correctness. Designing strong automated tests is necessary in order to make optimization refactoring without introducing regression bugs at the same time. Do you know the difference between service time and response time? Anyone? Just a few, OK. These 100 milliseconds here is the time it took for the service to process one incoming request. This is the service time. But it might very well be that the latency experienced by the users was actually 700 milliseconds. The user may have a slow connection, or the request could be waiting in a queue, while the server instance is already working at full capacity. This total latency is the response time, and it is always bigger than the service time, as it also includes the network round trip and the queuing time. So why am I saying all this, and what does it have to do with Go software? Let's illustrate with blue hexagons representing server components in Google Cloud. The point is that Go software are usually server components. The server components are where we have the most accessible information about performance, the server logs, the server traces, etc. But it's too easy to fool oneself into thinking that when the server is fast, then magically the whole system is fast and the users are having a pleasant, seamless experience, a responsive experience. That is simply not true. This is how, looking only at the server latencies of an internal application at Google, I didn't even notice that an important page was taking 30 seconds to render. The users were staring at a blank screen, completely unresponsive, while the JavaScript was performing UI repent over and over for some reason. And I had no idea, because that was completely invisible to the server monitoring. The first step to achieve some meaningful and valuable performance is a sane architecture that takes into account the client device workload, the browser cache, the network latency, and the number of network round trips. We should leverage usage metrics from the browser and not rely on the server metrics only. In the recent years, quite a lot of the workload and of the latency has shifted from the server side to the client side. And we have to take this fact into account. More generally, focusing on the users is a good idea. I can't overemphasize this axiom: users first. Now, let's have a look at some observability tooling available in a public cloud. We can usually view the access logs of all incoming requests, decorated with the applicative logs and the latency. This latency is, of course, the service time. It's super useful, but remember that it's only a fraction of the response time, because the server doesn't really know the full story, only what happens server side. If we are lucky, we can click on the latency and view a waterfall of all of the API calls that happen during the processing of this request. I love waterfall charts. They provide with so much insight in a single view. This trace shows me for a given request what API calls were made, how long they took, and if they were sequential or concurrent. I can also view the applicative logs right inside the waterfall diagram. This is actually a great feature for observability. The spans tell me what happened, and the logs tell me why. In this specific example, the total latency of 62 milliseconds consists almost entirely in one data store entity read and two data store queries. We also have a few read and write access to memcache, but those are super fast. Now I know that the bottleneck is the data store, and there's no point in trying to speed up my memcache operations. You can also notice that the last two data store queries are running concurrently, which is a good idea when it's possible. If you're using Google Cloud Platform, I strongly encourage you to set up the automatic export of all the logs to BigQuery. In BigQuery, you can use SQL to query fine-grained performance insights over large or short periods of time. So I will show you the backend of a website written in Go, running on Google App Engine standard. Okay, where is it? Okay, so in the latency column, I will zoom a bit. In the latency column, the static assets have extremely low latency, 1 millisecond, 5 milliseconds. They are actually served by an internal CDN, so static assets, JavaScript, HTML, etc. are fast. And here, if I click on an instrumented request, let's say this one, 120 milliseconds. Why is it so slow? I will see the API waterfall. Okay, so I know that this request, which took about 200 milliseconds, mostly consisted in a query to data store, and then a second query to data store. So this is quite helpful in helping me to determine why it was slow at that time. And then I could maybe investigate this query to determine what was the SQL or the precise request to know why it was slow or fast this time. I already have a sync to BigQuery properly configured. Where is it? This is a sync to BigQuery. You have to set it up. So I can ask questions like, in October, I will zoom a bit. So in October 2019-10, what are the most frequent URLs accessed, and what are their average latency and highest latency? Let me find the result. It takes just 5 or 6 seconds to compute. So I had here 5,000 requests to the home page, and on average, it's quite fast, like 36 milliseconds to view the home page. Sometimes up to 2 seconds for some reason. It's hosted on a serverless environment, so latency has some variability. And then the secondly most accessed is the RSS generation page 2,000 times, and it took on average 67 milliseconds. And the most slow was 650 milliseconds to display the RSS page. So this is really useful. Now, let's examine conceptually a typical waterfall of one incoming request. A waterfall like this one is the best view to understand the latency of a component. In this simple example, 100% of the server latency of a request, the service time, not the response time, consists in 6 sequential calls to external services. The service works well, but everyone agrees that it is a bit sluggish. Here I can see 4 opportunities for improvement. First, I now have a better idea of the latency of each of my dependencies. If my database access is expected to respond in under 100 milliseconds, but my measurements show that each query actually takes 200 milliseconds, then I know that something should be fixed in the external database. Maybe create a SQL index. If I'm lucky, I just sped up the database accesses without changing anything to the server code, only by doing ops on the database. And the total latency has just been reduced a bit. Next opportunity, look at the calls to service B. I often witness repeated access to the same service with different parameters and payload. It is a law of the universe that if the service accepts batch calls, that is, if it accepts many commands in a single API call, then the batch call will be faster than the sum of the individual calls. Here we are calling service B 3 times sequentially with different parameters 1, 2, 3, but we can do better. By transferring the same amount of inbound and outbound data and asking for the same amount of work to service B, but in a single API call, we suddenly improved the total latency. This may sound counterintuitive. However, it makes perfect sense because some heavy costs like network latency, component authentication, etc. are now paid only once instead of 3 times. We sometimes achieve this optimization by wrapping the command in a transaction. However, batching and transactions are different concepts. Transactions are about atomicity, while batching is about achieving economies of scale. This is what batching can look like when using a Go client library. Instead of 3 sequential calls storing 1 key entity per, we prepare a slice of keys and a slice of entities. The code change is not very complex. We just need to know that it happens to make things faster. Most of the time, it is also true that making a few API calls concurrently is faster than doing them sequentially. In my case, the calls to service B are logically completely independent from the database calls and from the email operation. So I can decide to run service B concurrently and save some milliseconds. The three other operations depend on each other's completion, so I can't run them all concurrently. As the batch call to service B starts immediately and is already finished when the email has been sent, it's effectively become free. The total duration is the same with or without the call to service B. For this simple example of parallelizing two independent blocks of code, I suggest to use a wait group. I don't recommend channels for this, because the channel's details are subtle and tricky to get right. Wait groups are straightforward. There are only three methods to know: add to increment, down to decrement, and wait to let the main coroutine move on when all the tasks are completed. Now, for the next opportunity, please ask yourself if the email sending operation is more synchronous or asynchronous by nature. I suggest that we postpone the work of sending the email after having sent the HTTP response of our human user, once again saving precious human milliseconds. If you have full control of your server instance, then it's super easy to launch this background work as a new Go routine. If you're in a managed serverless environment, however, it may be restricted and not possible to do any further work after the HTTP request has been processed. In this case, you'll have to use an asynchronous task queue. Deferring some work with task queues is more code than just launching a new Go routine. You have to create an asynchronous task, which typically involves serializing some parameters into the payload of an HTTP request that will be processed by another handler of your app. Now let's pause and see the result. A total of 200 milliseconds instead of 900 is a huge win. You can see that we achieved this without using any low-level assembly code, without upgrading the underlying hardware, and without even caring if we have one or many CPU cores. Now, a small interlude to say we should take our measurements with a grain of salt. In general, it is most useful to run the performance tests on the same machine configuration as used in production. Keep in mind that public clouds offer virtual machines, which are convenient, but don't give you full control over the underlying hardware. Even if you achieve very good average latencies, you may experience higher variance than with the dedicated hardware. This may perturb the tests, and in some cases, this may perturb the user experience. Here is a demo of a CPU and memory-intensive web app written in Go. It creates a mosaic in which each tile is a colored cat. My input image is the DevFest bus, and the little cat was drawn by myself. So, where is my mouse? This web app is hosted on Google App Engine Standard, on the smallest configuration option, F1. I need to specify two parameters, the resolution of a tile in pixels and the number of tiles that will make the width of the resulting mosaic. Let's generate a mosaic with an horizontal resolution of 20 cats, and each cat being 64 pixels wide. This should be fast if I do have internet. Do I have internet? Yes. OK, cool. That's not a super high resolution. Do you recognize a bus? Not really. OK, let's try again. With a higher resolution of, let's say, 120 cats. This will take a few more seconds. Obviously, I'm generating a much bigger image. And I will open, oh, server error. What happens? So I will open the logs here. That's in the Google Cloud Platform console. I knew this would make an error, trust me. That was part of the demo. So, what does it say? It says here, process, error, exceeded soft memory limit of 200 megabytes, because I'm on the F1 instant type, which doesn't have a lot of memory. Okay. So, I deployed the same web app on a bigger instance, F4, which has 1 gigabyte of memory. Let's open it in another tab. Here it is. I will ask for 120 horizontal cats. Generate. Please do work. It should work. 1 gigabyte of memory is plenty to generate an image with 120 cats of width. Yeah, very cool. So you can see that it's indeed made out of cats. And if I click, yes, we can read DevFest on the bus. This is great. So with a small instance, we can generate a poor resolution kitty mosaic. And with a bigger instance, we can get a bigger picture made out of much more kitties. Now, if I wanted to generate an even bigger file and have it printed in poster size, I would probably need more memory than what is available in the serverless options of App Engine standard. And we'll come back to this in a few minutes. So I will show you the source code of Mosaic, the name of this program. So the processing package is only able to take an image byte stream, so io.reader, in input, stamp it with little kitties everywhere, and write the resulting mosaic in an output byte stream, an io.writer. Then the command line executable reads the command line parameters and starts the processing using the file system, so it's not necessary to use a web app. Server.go is the web app, reading the HTTP request and outputting the resulting mosaic in the HTTP response. This is what I've been using today, deployed to App Engine standard. So in order to deploy to App Engine, I need 4 lines of YAML, app.yaml. And then if I wanted to deploy it to Kubernetes, for example, to Kubernetes Engine or to Cloud Run, I would need a Docker file. Here it is, just 4 lines of Docker file to copy my executable and maybe the PNG of the cat to the Docker container, and it works. And what's really interesting is that it's still the same processing function in my package, and the main application, the one of the server, is the exact same one that can run on my laptop or on App Engine standard or on Kubernetes Engine or Cloud Run without changing anything in the server, because it's an idiomatic Go server, and that's really nice to know. It's the same deployed anywhere. OK, back to the slides. I'd like to talk about serverless. Cold starts are a true performance concern in serverless applications. A cold start is when a request response time is much higher than usual because the server is warming up. Go servers tend to have fast cold starts, often under 2 seconds. And 2 seconds only to boot a virtual computer, start the operating system, and start my server. That's a pretty good cold start. Google announced Cloud Run this year at Next in San Francisco, which lets you deploy your own containers to a serverless platform. With Cloud Run on GKE, for example, you can achieve vertical scalability by choosing your custom machine types with more memory and more CPU cores, and still scale to 0 in a serverless way. This solved my problem of generating a huge mosaic file and printing it as a 2-meter high poster in high resolution. True story. Now let's have a look at the Go tooling. The tools I'm going to show are not specific to the cloud. They can run on your development laptop, and they can run on virtual machines as well. It's perfectly fine to do some performance exploration on your own computer, but remember that it's more relevant to run them in a production environment. Also, the measurements in production sometimes dispel the workstation measurements, as well as my best intuitions. In Go, this is how you run the automated tests. All Go programmers are familiar with this command line. I encourage to explore performance in test files, as the standard testing package plays very nicely with the performance tooling. My demo today uses Go test, but remember that the same tools can be used for any Go executable or server. This is how you run your benchmarks, integrated in the Go test subcommand with an additional flag. This is a powerful performance feature of the Go tooling. Write two benchmarks calling A and B respectively, and see which one is the fastest. Here are two functions, A and B, which do the same thing. Where is my... Just a sec, OK. A is here, B is here. They do the same thing. They determine if the word database is contained in this article. Function A uses a regular expression for this, which is already compiled. And function B uses the standard library function string.contains. Is it readable or not really? Not really. Is this better? OK, so this one, A, regular expression, B, string.contains. I will now run the test and the benchmarks. Yay, tests are passing. More precisely, test A is passing and test B is passing. Now let's run the benchmarks. So what is it telling us? It says that function A was run 10 million times and took 200 nanoseconds on average. Function B was run 20 million times and took 100 nanoseconds on average. OK. So this means that in this case, the standard library function string.contains is twice as fast as a regular expression. This is good to know. Benchmarks give raw numbers. Now we'll see two graphical visualization tools. Trace is an execution tracer. It works by instrumenting the program to produce a binary file containing the activity of each CPU core over a period of time. Is it idle? Is it running the garbage collector? Is it running a function? And what is the call trace? This is a CPU-bound sequential task. You can see that only one of my CPU cores is active, and the other ones are idle. It turns out that the same sequential computation may be dispatched on several CPU cores by the scheduler of the Go runtime. This doesn't involve any concurrency. Only one CPU core is working at any given time. Now, this is an example of a concurrent computation using several Go routines. You can see that all the cores are busy. This can be good or bad, but it doesn't mean that the program is efficient. Having a lot of Go routines communicating and synchronizing with each other can lead to contention and to a lot of expensive context switching. Quite often, an inappropriate granularity for the Go routines can lead to worse performance with 4 CPU cores than the same sequential task on one single CPU core. The best multi-core performance is achieved when each Go routine performs a fair amount of sequential work before writing the result to a channel, or releasing a mutex, or decrementing a weight group. I will show you the execution trace of the benchmark of the cat Mosaic process package. So let's run the benchmark. HTTP 6060, that's for my window on the right. I will produce a binary file. Okay, not branch, bench. HTTP, and I will use -trace to a file a.out. Whoops, doesn't work. Go test, bench, HTTP 6060, trace. What's wrong with that? Seriously. Can anyone see any syntax error in that? Where is the space? Yes, I don't know. Nope. Okay, so that's over 1 minute of nonsense. No test to run, that's right. I only have benchmarks here. Oh, okay. I'm not supposed actually to say HTTP 6060. That's only for the visualization part. So just generate a.out, a binary file of the trace. Sorry for that. It's a live demo. Okay, now the visualization. I'm not interested at all in the numbers, the results of the benchmark, because the numbers are skewed by the instrumentation. Right now, I'm interested only in the visualization of the trace. Go to trace, HTTP 6060, that's for the window on the right, with the file a.out. Cool, what do we have here? The benchmark has run for about 3 seconds, so I have a slice time of about 3 seconds, and my laptop has 4 CPU cores, so I have 4 lines, one for each CPU core. I can see at any given time what the processor were doing, and this looks actually like a sequential computation. Only one CPU core is active at any given time because my code, which generates a mosaic, is sequential. So I can click here and see what the processor was doing. It was calling the function write image in the PNG encoder function of the standard library. Here, what was it doing? Decoding some JPEG. Yes, because it takes the input, processes it, and writes the outputs over and over dozens of times in the benchmark. So there is no specific order here between encoding and decoding. At any given time, I can click and discover what the hell it was doing at that instant. This is really useful. Our next graphical visualization tool is the Pprof Viewer. Pprof is the profiling data format available out of the box in Go. Let's have a look at the Pprof CPU profiler. The CPU profiling works by sampling. It incurs a relatively small runtime overhead. Every now and then, the kernel sends a SIGPROF signal, and the special handler of the Go runtime gathers the call trace of one currently running Go routine. The dataset of all these call traces over a period of time contains rich statistical information that is used to produce a graph of the functions showing who calls who and how much time is spent in each function. In the resulting graph, you can't read now, but I will zoom in a minute, I promise. Each box is a function and explicitly displays the number of seconds spent inside the code of this function, the total time spent in this function, including its own function calls, and the equivalent percentage of the total execution time recorded. Running the benchmarks is a very effective way to gather this information because the same functions are run over and over in a short period of time. At the top, you will find the program's entry point and your own important functions. And at the bottom are all the standard library functions and the system calls. The duration for each box consists in the sum of its own CPU time plus all the CPU times of the function it calls downstream. This counts only the time actually spent using the CPU, not the time spent waiting for something, waiting for the hard drive or waiting for the network. So I will once again run the benchmarks. This time instrumented with CPU profile to produce a file a.prof. Should take no more than 3 or 4 seconds. OK, now the visualization is go tool Pprof with HTTP 6060. That's just for my window. It's optional. a.prof. OK. I'm not interested, once again, in the numbers of the benchmark here. I don't care. I just want the visualization. So what do we have here? The processing package in my Mosaic generation package accounts for 88% of the total execution time, in which, let's see, reading an image and decoding it as input took 13% of the total time. My function colorizeCat, which is the one which actually contains my business logic to apply kitties on the image, is 20% of the total time. And PNG encoding at the end of the processing accounts for 51% of the total time. This is highly valuable insight. If I wanted to optimize my own code, now I know that I would only be able to optimize less than 25% of the total execution time. So I could reduce 20 to, I don't know, 15 or 10, but I wouldn't gain much. Shoot, I lost my visualization. What I know now is that the PNG encoding function, which is part of the standard library, accounts for more than 50% of the total execution time. This is the bottleneck. Now that I know that encoding to PNG is the bottleneck, what can I do? I cannot really parallelize it because PNG encoding of the picture is called only once at the end of the processing function. What I can do is to decide to not buffer the output. So this was my previous code. This is what I do now, processing, with whose second parameter is W, which is the response writer of my web app. The only advantage of buffering in my previous code was to log the precise number of bytes written. I can live without it. OK, let's get rid of that. If I give the response writer directly to the process function, the browser will now receive the stream data as it is being encoded. This is good UX feedback because the user sees the first kitties displayed much sooner than before. It also greatly improves the total response time because the encoding is effectively parallelized with the response being downloaded by the client, by the browser. As I mentioned earlier, everyone has intuitions about the expected performance. There is also sometimes some emotional investment and some prejudice on this topic. I suggest to stick to the facts and to discover the current bottleneck. What takes the most time in my use case? Everything that is not the bottleneck can wait. I will have to hurry up, and if you have questions after the session, I'll stick around a bit with you. Have you heard of flame graphs? A flame graph is a fancy way to visualize the profiling data. It was invented by Brendan Gregg around 2013. It's not completely obvious the first time we see a flame graph, but the horizontal x-axis doesn't represent the chronological time. However, the width of each span is proportional to the duration spent executing a function. An interactive flame graph is provided with the GoTool Pprof web viewer. It uses the same binary data as the Pprof graph. I can select any function I want. So encoding. OK, process. This is when I'm processing the kitties. And PNG encoding. I can dig deeper and deeper as much as I want to see why PNG encoding seems to be slow in the standard library. OK. So I can discover the internal latencies of any function. Why should I look at a flame graph if it basically displays the same information as the regular Pprof graph? Here is a fictional case. This is a stereotypical work day. Work in the morning, work in the afternoon, and sleep all night. This is a stereotypical vacation day. Sleep in the morning, go to the beach in the afternoon, and dance all night. And this is what the Pprof graph looks like if you run a simulation containing some people in activity and some people in vacation. Some functions, for example, sleep, are called by everyone, just not at the same time of the day. Even with a complete set of duration annotations, this graph doesn't give enough information to know if going to the beach is part of the work days or part of vacation days or both. Maybe some employees prefer to skip work. This flame graph, built out of the same profiling information, quickly gives the answer. The beach activity is properly stacked only under the vacation day. We also discover that the vacation day contains a bit more sleep than a typical work day. Bottom line, flame graphs are super useful, very beautiful, like a campfire, and very useful to find the root cause of latency issues. Now a word about concurrency, because Gophers love concurrency with Go routines and channels and stuff. Concurrency and parallelism are powerful tools to do several things at once and help decrease the total latency of a request. As we've seen, a lot of the time spent in a web service is spent waiting for an API call to return. In this case, the performance is not related at all to the number of CPU cores, and also not related to the speed of each CPU core. It is, however, extremely useful to be able to call several external APIs concurrently. This command runs the test with a special instrumented binary version that detects race condition. And what does it have to do with performance? The point is, the race detector is necessary to stay safe for the same reason that the tests are necessary to stay safe. Introducing concurrency and parallelism in order to run faster may lead to complex code and to subtle bugs. There is no such thing as a harmless data race in Go. We have to be careful. And now the part that you've all been waiting for. Thank you for being still there, by the way. Here is the checklist of common performance bottlenecks and how we can address them in Go. You can take pictures if you want to. What should you do if your code is already fast? I strongly recommend not to optimize too early, not to try to optimize everything, and above all, not to turn your code into a giant spaghetti monster just for the sake of performance. Please don't. However, if your code is not fast enough, look at the ever-popular execution of useless instructions. Obviously, hunting and eliminating useless code is a good thing. Please do it. The big O analysis of a function is its theoretical runtime complexity. Big O analysis is the golden metric at the university and also in some job interviews. In my experience, big O is not always helpful and can even be misleading. Of course, if your function is quadratic or cubic, then you probably won't be able to go very far and a better algorithm may be needed. However, in my experience, dirty, slow code and clean, efficient code often have the same exact time complexity. The real difference is how the efficient code successfully gets rid of all of the clutter that we commonly sweep under the carpet of irrelevant hidden multipliers. Network I/O and external API calls are relatively extremely expensive. My advice is to make as few requests as possible and not to block everything while waiting for a network response. I'm sorry, I'm going fast. I only have 5 minutes left. Reading from and writing to the file system is slower than most of what we do in memory and in the CPU. My advice is to work as much as you can in memory and to do your input-output in a non-blocking way. Contention. Thousands of Go routines waiting for each other is a perfect recipe for unnecessary slowness. To limit the excessive need for constant communication between Go routines, I suggest to create workers. The worker pattern looks like this. If I have 4 CPU cores and 1 million computations to perform, I could launch 1 million Go routines, which has a cost in scheduling and in synchronization to gather the results. But it's more efficient to start a small number of worker Go routines, say 8, and have each worker process 1/8 of the total loads sequentially. Asking for memory to the operating system and to the Go runtime is a notoriously slow operation. My advice is to allocate large chunks of memory in one single call to the built-in make function, to reuse memory by passing buffers as arguments to the processing functions, and also sometimes recycling objects by using a pool from the sync package can prove very useful. For example, allocating upfront, here, one call to the built-in function make, is more efficient than allocating many times in a loop with the function append. Heap or stack. This part is specific to the Go compiler. We know that allocating in the heap is expensive, and that allocating on the stack is almost free. But what goes in the heap and what goes to the stack? The answer is not intuitive. Some local variable may escape to the heap if we take its reference and pass it around. These commands prove scientifically that the Go language specification does not say anywhere if memory is allocated on the stack or in the heap. In fact, the spec contains 0 occurrence of the words stack and heap. In the end, it depends if the compiler is clever enough to prove that a variable doesn't escape, so it is safe to put it on the stack. Use this extra GC flag to determine which local variables escape or not. You may then try to adapt the function scope to leak less references. Regular expressions are great, but they are often overkill for a given need. In this example, extracting words separated by a slash is more legible and more efficient if we use the standard library function strings.split instead of a regular expression. My advice is basically to avoid regular expressions when you can. You can often get better results using the standard packages strings and bytes, or writing your own for loop. A function call incurs a non-zero cost, which can be significant if the function is very small and called millions of times over and over. The compiler is able to inline some small functions, which means to copy and paste the body of the function instead of actually making a function call. This function on the left will not be inlined. But if you, as a developer, write this equivalent function on the right, then the compiler will inline it, effectively saving the cost of a function call. The language specification does not talk at all about inlining. The compiler has its own very specific internal rules when it comes to decide if a small function will be inlined or not. chasing the compiler, chasing the inliner to have it inline a specific hot function has become a popular sport. Before I finish, I'd like to thank my colleague David Gageot for his wonderful presentation tool DemoIt, which I'm using today. There is a feedback wall, and we love feedback stickers. Here is my takeaway. The Go language was designed for cloud computing with scalability in mind. Its ecosystem is rich, and the performance tooling is really good. Now, to improve the experience of your users and make the world a better place, start with an important use case, discover the bottleneck, fix it, and repeat. Thank you very much for listening.